All right, so we got through, we're on the back of the second page. That's correct, right? We're right here? Okay, awesome. So we've got the log functions. Logs were brand new to you in Algebra 2. Logs, and we talked about the square root function being related to the quadratic, the cube root function being related to the cubic, right? And then, and how are they related? They're what of each other? Starts with an I. Inverses. Okay, good. So the log function is the inverse of what? Exponential. Very good. Okay, so because exponentials and logs went together, right? That's when you learned them. So going to give you a quick kind of little reminder of something. You could have, let's go over here, and you don't have to write this down, just stay with me. I could have f of x equals log base 8 of x, right? That's not what goes in that blank there, so don't write that down. But that's what a parent log function would look like. We agree with that? All right, so if I said, all right, I want you to substitute in 5. What's log base 8 of 5? Do y'all know? No, neither do I. You're not going to know unless you Rain Man or have a calculator, so that's fine. But we do need to be able to calculate some points without a calculator to get, you know, a good sketch of a graph if we're not sure what our anchor points are. So so you can take this, and I'm not actually taking the inverse. It is the inverse of an exponential, but I'm not going to take the inverse, but I can rewrite it. I can rewrite a log function as an exponential function. So I'm going to start by saying y equals log base 8 of x, and just change that to y so it looks a little bit better. If I want to write this as an exponential instead of as a log, what would be the base of my exponential expression? What's the base of my log? 8. The base of my exponential expression is 8. This is the base, right? So I start with 8 to some power. What would be the power on the 8? The base to this power is always equal to that argument. Okay? That's how you rewrite a log as an exponential every single. If you need to jot this down somewhere, that might not be a bad idea. I'm trying to think of where. Maybe up at the top. I know it's kind of skinny, but I'm afraid if you write down here, it's where you're going to glue. But you could write it up here. You could have to write it like horizontally, sorry, instead of keeping it. But that's how you rewrite them. That's important because when you go to graph things and you're going to make a t-table, which we don't always make t-tables, but if you were going to do that, then we usually choose some x's, and then we figure out what y is, right? Because that's your little function machine. X is the input, y is the output. Well, same thing here. If I said x is 5, what's y? Guess what? You still don't know. You still can't figure it out by hand in an easy fashion anyway. But if I chose some numbers, instead of choosing my x's, I could choose my y's, right? Because here, if y is 1, what is x? 8. So that gives me the ordered pair of 8, 1. Does that make sense to you? If y is 0, what would x be? What's 1? Because anything to the 0 power is 1. If y is negative 1, what would x be? It's a fraction. The negative exponent makes it the reciprocal, right? So 8 to the negative 1 power would be 1/8, right? So that gives me 3 points on my graph right there. You see how easy that was? And it's easier to think through this way than it is to think through this way. Okay? So you need to remember that we can rewrite them. We may not always need to do that when we're graphing. That's why we have the anchor points, so we can just use those. But this is something that we have to make sure we've seen before and makes a little bit of sense to us. Okay? So let's go back and talk about the parent function. So this parent function is not log base 8. Okay? What am I? This right here. It's not log base 8. And you might not necessarily have enough knowledge to know what it is without me giving you some information. But if I don't write a base on there at all, what is the base? 10. So this is actually f of x equals log of x. So it's log base 10. That's why we don't write it. But just like with the exponentials, we wrote a 2, but I could have a parent function of 5 to the x. My parent function could be log base 8 of x. This one just isn't. This is what this graph actually is. Okay? So can you substitute? Can you take the log of a negative number? No, you can't. You cannot take the log of a negative number because guess what? If I could take the log of a negative number, that would mean that x could be negative, right? Is there any power that I can take 8 to that would give me a negative number? Nope. And that's why you can't take the log of a negative number. Okay? Because when you rewrite it, like you're not going to get that as the other value at all. All right. So over here again. this is what I have, then my domain starts where? Since I can't have a negative x. 0. And it's going to go to infinity. Do I include 0? No, I do not. What's my range? Negative infinity to infinity. Do I have any x-intercepts? Yes. 1, 0. Right here, right? That's my x-intercept. It's 1, 0. And every parent log function, I don't care what the base is going to go through 1, 0. Because it's going to be where you would have a 0 exponent and you get 1 out. Do we have any y-intercepts? Nope. None. Because we don't include that 0, right? Do I have any extrema? Nope, no critical points at all, so none. Is it increasing anywhere? Yes, from 0 to infinity, right? Is it decreasing anywhere? Nope, so it's none. In behavior, as x approaches infinity, f of x approaches what? Infinity. Does x approach negative infinity? No. So remember we talked about yesterday, so we just don't even talk about it. We only have half of it to talk about. Are there any discontinuities? Nope, none. Even, odd, or neither? Neither. Everybody okay so far? All right, so we need some anchor points. Our anchor points are going to look like this. Well, this 1, 0 for sure. Since this is log base 10 of x, if your base and your argument are the same, so like log base 10 of 10 is 1, because that's like taking it to the first power there. So I'm definitely going to use 10, 1 out here that I can draw. Then I can also use this, which gives me a negative 1 for y. What do you think this x value would be? Because it's not 0. 1/10, okay? Because, you know, if we rewrote it as an exponential. So I can use the x value of 1/10. I'm getting that from my base. My y value would be negative 1. My x value is 1. Y value is 0. X value of 10 gives me 1. Because these are the ordered pairs that we got from our other one, right? When it was base 8, this was 1/8, and this was 8. Right? It just changes based on the base. And that'll get a little bit better if it feels kind of a little bit weird for you right now. Any questions so far? All right, so what else does this graph have that we haven't talked about? Asymptote. There's an asymptote here. If you had Mrs. Archer last year, it's an asymptote, but it's not an asymptote. It's an asymptote. So asymptote. Not exactly. Not exactly. But asymptote. And what is that asymptote? X equals 0. Very good. Everybody good so far? So we have a second logarithmic. These two are not inverses of each other, but what happened? There's a reflection, good, in the x-axis. So this is still an f of x equals log of something, but in this case, since this is actually a reflection of the one above it, this is f of x equals log base 1/10 of x. So when your base is less than 1 but greater than 0, then it's just reflected in the x-axis. Okay, looks the same, it just goes the other way. So our domain here still goes from 0 to infinity, and I don't include either one. Range is still negative infinity to infinity. Are there any x-intercepts? Yes, 1, 0. So it's the same. Regardless of the base, the parent log function goes through 1, 0, period, whether the base is a fraction or not. Y-intercept? None. It does not go through anything. Any extrema? Nope. Increasing anywhere? Nope. It's decreasing the whole time. So from 0 to infinity. Okay. In behavior, as x approaches infinity, f of x approaches what? Negative infinity. Okay, discontinuities, are there any? Nope, there are none. Even, odd, or neither? Neither. So, anchor points. I'm using this one for sure. I can use this one, and I can use one out here I can't see. This is just a reflection of the other one over there, right? So what's this x value? 1/10, which means our y value is just 1. And then this is 1, 0. And then what do you think this is going to be? 10, negative 1. Okay, everybody good with all that? Any questions at all? Alrighty, so then I also still have an asymptote, right? So my asymptote is at x equals 0 again. Everybody good? All right. Any questions? Then we have the new weird looking one, right? Which is really not that bad. It's just actually kind of interesting. So this one is not traditionally lumped with the rest of the parent functions, but it is something that Mr. Ackerman requested that we put in because you need it for calculus, and when that's the first time you've ever seen it, it just seems so weird. It's just kind of weird. We're just introducing it. We're going to look at it. We can actually do a little bit of transformations with it. The application of it, we're not going to use it all. So it's just kind of an introduction to it, so it won't be brand new to you, whether you take calculus next year or whenever, in case you ever need it. But so this one is interesting in a few different ways. First of all, it's piecewise, which some of you may have not dealt with any piecewise before. It's a piecewise function, and it doesn't look like the rest. Is it a function, though? Yes, it passes the vertical line test. I can write it as f of x. But you can also write it differently. So we're going to write it the different way just so that you see different things. Since it's signum and it's kind of a special thing to its own, we use SGN, that's SGN, kind of an abbreviation of signum, of x. The equation looks like, one of the ways you can write the equation is like this. The absolute value of x over x. So if I substituted in a negative 3, absolute value of negative 3 is 3. Over a negative 3 gives me a negative 1, right? So at negative 3, I'm at negative 1, and that would work for all of them. If you substitute in a positive number, you're over here. Algebraically, what happens when you substitute in 0? Can you divide by 0? No, it's undefined, even if 0 is the numerator. So it's this, but of course, x can't equal 0. But then there's usually another little disclaimer on there about what happens when x does equal 0, because there is a point there. But, interestingly enough, when you actually apply this and use it, most of the time you don't even care about that 0, so it just gets ignored anyway. It is part of the function, so we're going to use it when we rewrite it a different way. So another way to write it is piecewise. If you were in pre-AP last year, you did piecewise functions. If you were not in pre-AP Algebra 2, then you didn't. And so this might look a little bit weird to probably all of you, but we're going to talk about piecewise more next week, so don't freak out. I will make it more clear completely, I promise. But so SGN of x again. So when I want to talk, and it's called piecewise because it's like 3 pieces, right? This side, just if I look at what's happening in these 2 quadrants and I ignore all the rest of that, that's just a horizontal line, right? Which means y equals negative 1. But y doesn't always equal negative 1, only until it gets to here, right? So we have to split this up. So we use the squiggly brackets, but it's kind of big because we're going to list some stuff right here. So the signum of x, or y equals, same thing, negative 1, but not forever. It only equals negative 1 if x is less than 0. So that takes care of this piece right here. Then I have to take care of this point. I can say this equals 0, but not forever, only if x equals 0. And then I can say it equals 1, but not for the whole time, only when x is greater than 0. Okay, everybody okay with that so far? So piecewise, because you got 3 pieces to get 1 function. You can just snap them all together and you make your graph. Okay? We'll talk about piecewise more because I know that may be the first time you've ever seen one like that. But we can write it either way. To do the rest of this, we're looking at the graph anyway. So let's talk about domain. What is my domain? Negative infinity to infinity. Good. It is all those real numbers there. What about the range? Okay, I heard a couple of different things. If I say the interval -1 to 1, that implies that 0.5 is part of my range. Is 0.5 part of my range? No, it's not. So even if I just said, like when we're talking about domain, obviously that's an infinite domain, we're going to infinity. But even if I just said my domain was from -4 to -2, that's still an infinite domain because there's an infinite number of points in there, right? This is a finite range, meaning it's countable. I can actually count them. There are only 3 numbers, not an infinite amount, 3 numbers that live in my range. So when you have a finite domain or a finite range, then it makes way more sense to put it in set notation. Because you have, and I heard somebody say it, all I have for my range is -1, 0, and 1. That's it. There's no in between. Kind of like people on a bus. That's a finite number, right? You're not going to have half a person on the bus. If so, somebody's going to call the police, right? So that's it. We good? All right. Do we have any x-intercepts? I don't know. Okay, hey, I don't know is a valid answer. I am fine with I don't know. Is there a point that crosses the x-axis? Yes, it's right there. And so that is 0, 0. And it may seem weird, but that's where your point is that crosses the x-axis. Do we have a point on the y-axis? Yes, the origin again. Do we have any extrema? No, because there's not one point that has the highest or the lowest y value. There are an infinite number of those points. So we're just not even going to put anything because really extrema isn't even anything we talk about with this one because this one doesn't exactly fit the mold of the rest of them. I just kind of copied and pasted all this. We're just going to leave this completely blank. Is it increasing anywhere? No, so there's none. Is it decreasing? No. But what this one does have that the other ones didn't, and that's why it's not even a choice, is constant. So I have some constant intervals. This graph is constant from -infinity to 0. 0 doesn't count because there's just 1 point, so it can't be constant if it is just one thing. And then from 0 to infinity. End behavior. So as x approaches infinity, f of x approaches 1, which may seem a little bit weird because not only do we approach it, we're already there, but even when you talk about limits, you can either actually be able to get there or not be able to get there. We probably wouldn't exactly talk about end behavior in this case anyway, but we'll fill it in. That's why it seems weird because it's not even anything that would really come up. But as x approaches -infinity, f of x approaches -1. Are there any discontinuities? Yeah, jump. Okay, so we got jump discontinuity. Where? X equals 0. When you have discontinuities, their location is always an x value. It's not an ordered pair, even if it's removable. Okay? Even or odd or neither? It is odd. And not only just because you can rotate it 180 degrees, but I can also substitute in that -x. F of -x equals the absolute value of -x over -x, which is the absolute value of x over -x. And that is negative f of x. So you can figure it out algebraically as well. Okay. Any questions at this point? Are we good? Yes? Okay. All right. So I'm not going to try and start on the yellow paper. I wasn't sure if we'd have time or not, but I just wanted to go ahead and have it. So I don't want you to glue in the yellow one yet. I wouldn't.
Good afternoon, Maverick.
You can glue in the pink ones.
I have an important announcement. We are going to announce our upcoming course.
Look over this so you're familiar with it for Monday, okay?